Hey everyone, Geek37 back with another video. This is part 11 in my Exploring the Heptagonal Triangle series. And in yesterday's last video, I derived the above identity where a squared plus b squared plus c squared equals 7 times r squared, where a, b, and c were the lengths of the heptagonal triangle, and r was the circumradius of the heptagonal triangle. It's also the circumradius of the regular heptagon as well. What we're going to do today is we're going to do a little bit more with this particular identity, and we're going to derive another trig identity from it. So what I'm going to start off with is I'm going to do something interesting here. I'm going to rearrange this statement so I get b squared plus c squared, and then I'm going to do plus a squared after that, and I'm going to put a little spacing between this here to get 7r squared. Now, what am I doing? I am going to add in 2bc right here. And over on the other side here, I'm going to take away 2a squared, add 2a squared, and I also have to take away 2bc in order for this equation to remain balanced on the left side. I'm not doing anything to the right side. I'm adding and subtracting the same amounts in order to keep the original equation balanced. Now here's what happens. The first three terms turn out to be a perfect square trinomial, namely b plus c quantity squared. And then what I'm going to do next is I'm going to take away the a squared. So the negative, I'm taking away a squared because I'm taking a squared minus 2a squared to get that. And then after that, I get plus 2a squared minus 2bc, and that will equal 7r squared. Now, where do I go from here? What happens is I'll rewrite the first part of the equation down, and then I'm going to factor out a positive 2. So I'll get a squared minus bc equaling 7r squared. Now here's what happens. We know for a fact that BC is equal to AB plus AC, just like so here. So what I'm going to do with the BC right here that I'm underlining, let me maybe highlight that. This BC right here, what I'm going to do is I'm going to rewrite the equation as follows. I'm going to write it as B plus C quantity squared minus A squared plus 2 a squared. Now I'm going to have to do a negative here because I have a positive version. So it's going to be minus AB, minus AC equals 7r squared. Make sure I had that written down correctly. Now what I'm going to do next is I'm going to factor out a positive a. So I'll have b squared, b plus c quantity squared minus a squared plus 2a. And then I'll have a minus b minus c equals the 7r squared here. Now, the interesting thing is I still need to do one more factoring on this second set of parentheses. What I'm going to do is I'm also going to factor out a negative because I need to do this so I can do another factoring properly. So I'll pull out the negative, so I'll get a negative 2a, and what will happen is the b and the c on the inside of that second set of parentheses becomes positive and the a becomes negative. Now, where do I go from here? Well, believe it or not, this part that I'm going to mark here in pink, you see the b plus c quantity squared minus a squared. That itself is a difference of squares. So what happens is I can rewrite that as b plus c minus a times b plus c plus a minus 2a in parentheses b plus c minus a equals 7r squared. Now, what will happen next is since I have the same set of parentheses here, I can actually do this. I can rewrite this as b plus c minus a, and then in the next set of parentheses, I can write b plus c plus a minus 2a equals 7r squared. Now what's next? Well, as you can see in the second set of parentheses, I have a minus 2a, so I'm going to get b plus c minus a, b plus c minus a equals 7r squared, just like so here. Let me erase this quick so we'll get it out of the way. Go over here and rewrite it because we did use it. So now here's what happens. I have b plus c minus a equals 7r squared. I could take a square root to both sides here, get rid of that, keep the principal square root, b plus c minus a, and I get the square root of 7 times r. And this is a even nicer relation compared to the one that I derived in the last one. B plus c minus a equals 7 times the square root of r. I didn't realize this until after I had tried playing with this to see what would happen when I derived it, and I got this nice little identity here. And now what I'm going to do next is I'm going to use this identity to derive another trig identity. Okay, now that I have my screen clear, I have b plus c minus a equals the square root of 7 times r. Now what I'm going to do is I'm going to derive the trig identity from it by dividing everything by 2r here. Now, if you remember from the other videos in my list, you'll notice that whenever I divided any of those, the first three variables by 2r, I am creating a sign ratio. And what happens is I'm going to get the sine of 2 pi over 7 plus the sine of 4 pi over 7 minus the sine of pi over 7. The r's will cancel on the right side, and that will equal the square root of 7 over 2. So that is a sine ratio where I have the sum of the two larger sines minus the sum of the smaller sine, or minus the smaller sine to get that. And of course, if we were to include in instead of the 4 pi over 7, we can replace that with the 3 pi over 7, which I showed that the sine of 4 pi over 7 is equivalent to the 3 pi over 7 because 4 pi over 7 plus 3 pi over 7 equals pi. I can subtract off the pi over 7, and that will leave me with the same amount as before. And that will conclude the video. The reason I wanted to show you this today is because this could qualify as a Math Olympiad problem. If you start with the given identity, you can derive the analog where it's instead of r squared, you get the r and the b plus c minus a on the left side. And then dividing by 2r, you can get those different sign ratios. You don't have to do a lot of trig work to get through it, but I just wanted to show you that today. I hope you enjoyed this video. This is Geek37 signing off.